This is stochastic processes, Mod-08 renewal processes, Lecture 2 generalized renewal processes and renewal limit theorems. In the lecture 1 we have discussed the renewal processes, definition and its properties, followed by renewal process definition we have discussed the renewal function, and then we have discussed the renewal equation, and also we have seen a few examples in the lecture 1. In the lecture 2 we are planning to discuss the reward renewal process. As a special case we are going to discuss the Markov reward models. Then we are going to discuss two different renewal processes, that is alternative renewal process and delayed renewal process. With this we are completing the generalized renewal processes. The second half we are going to discuss the central limit theorem, long run properties and the three important renewal limit theorems. What is a reward renewal process? Let x1 be the time to the first renewal and let xn be the time between n-1th renewal and nth renewal. The same definition which we have used for the renewal process. And also you assume that xi's are IID random variables with the CD of capital F of x. Since xi's are the inter-arrival times, the mean will be a positive. Mean exists and it will be positive. Let Rn be the nth reward at time t of the nth renewal. For each renewal you are attaching the reward at the time of the renewal. Usually Rn may depend on Xn. Now we are defining a new random variable R of t, function of t, that is nothing but the summation of Rn's, where n is running from 1 to n of t, where n of t is a renewal process. The collection of R of t for t greater than or equal to 0 will be called it as a reward renewal process. That R of t is nothing but a reward earned by time t. So from the renewal process we are attaching the reward for each renewal, and by defining R of t is equal to summation of n is equal to 1 to n of t Rn, that will be called it as a reward renewal process. Note that unlike the Xn, each Rn may take a negative values as well as the positive values. The Xi's are nothing but the inter-arrival time of the renewals, whereas the rewards may take negative values as well as positive values. See the sample path of a reward renewal process. So the x-axis is the time, the y-axis is n of t, and these are all the time points in which the renewals takes place. The first renewal takes place, second renewal and so on. So this is the inter-arrival time, and attaching the reward Ri to the each xn. And these Ri's may be negative or positive, then the collection of Ri's with this form Rt is equal to summation n is equal to 1 to n of t Rn will be the reward renewal process. So it is very difficult to show the sample path of R of t. So here we are showing the sample path of renewal process with the rewards attached with the each exercise. Now we are moving into the simple example of reward renewal process. Consider an age replacement model. In this model, a component that is used continuously with replacements. Let x be the lifetime of the component, which is random with the distribution function f. The component is replaced by a new one upon failure or at a fixed time period capital T, whichever comes first. The replacement policy is called the age replacement because the component is replaced by a new one upon failure or at a fixed time period T. The cost of a new component is C1 and the additional cost is incurred by a failure is C2. Our interest is to find the long run average cost. Let NT be the number of replacements of components by time. N of t is a renewal process. Let R of t be the amount of cost incurred by time t. So this is a reward renewal process. So the long run average cost can be expressed as the ratio of expectation of R by expectation of X, that we are going to conclude later. Now we are using the long run average cost is the expectation of R divided by expectation of X. Expectation of R is nothing but expectation of cost during a cycle, and expectation of X is nothing but expectation of cycle length. Now one can find the expectation of cycle length, that is nothing but the expectation of the cycle length is a random variable which is nothing but the minimum of x or t. Here the component is replaces either upon a failure or at age capital T. Time between replacement is called a cycle, that is nothing but the integration 0 to t 1 minus f of x dx. Given that the reward or cost during the cycle R, therefore R will be C1 if x is greater than t. If it fails after t, if it fails before t, then there is additional cost C2, therefore the cost will be C1 plus C2 if failure occurs before the fixed time t. Hence the expected value, that is the expected cost, is either C1 with the probability x is greater than t, or C2 plus C1 plus C2 with the probability x is less than or equal to t. So that is nothing but C1 plus C2 times f of t. Hence the long run average cost is nothing but expectation of R divided by expectation of x, that is nothing but expectation of cost during a cycle divided by expectation of cycle length. Substitute the values, you will get the long run average cost. Now we are moving into the special case of reward renewal process, that is a Markov reward model. A Markov reward model is a labeled continuous time Markov chain augmented with a state reward and impulse reward structures. The state reward structure is a function R that assigns to each state a reward R suffix S such that if t time units are spent in the state S, a reward of Rs times t is occurred. The rewards that are defined in the state reward structure can be interpreted in various ways. They can be recorded as the gain or benefit occurred by staying in some state, and they can also be regarded as the cost spent by staying in some state. And this type of Markov reward model is called rate based Markov reward model. The impulse reward structure, on the other hand, is a function of function tau that assigns to each transition from S to S dash, where S and S dash are belonging to the state space S, and the spending time in transition of S to S dash is positive, and the reward tau of S to S dash such that if the transition from S to S dash occurs, a reward of tau S of S comma S dash is occurred. Similar to the state reward structure, the impulse reward structure can be interpreted in various ways. An impulse reward can be considered as the cost of taking a transition or the gain that is occurred by taking the transition. Markov reward models are commonly used for the performance, dependability and performability analysis of computer and communication systems. In general, the reward rate is assigned on the basis of desired measures. Let z of t is nothing but r suffix xt be the instantaneous reward rate of the Markov reward model at time t, then the expected instantaneous reward rate at time t is given by expectation of z of t, that is nothing but summation of ri's pa of t. The expected reward rate in steady state is nothing but expectation of z is summation of ri pi I. Suppose in the perform availability model, our interest is to find out the availability of the system, then one can assign the rewards for the up states are 1 and the rewards for the down states are zeros, then the expected reward rate will be the availability for the system by making a summation of ri's and the probability of being in those states. The different types of measures, namely steady state measures, transient measures, cumulative measures and performability measures, are supported by Markov reward models. For instance, steady state measures are computed from the steady state behavior of the Markov chain. So, for the availability model, if you know the steady state behavior of the Markov chain, such as a steady state probability of being in this system, then by assigning the rewards 1 to the up states and zeros to the down states, one can get the steady state availability of the system. Similarly, reverting the rewards, you can get the steady state unavailability of the system also. Under the assumption that the steady state distribution of xt, one can find the steady state measures by multiplying ri's with the pi i's, where I is I belonging to the state space S. Similarly, the cumulative measures denoted by y of t expressed overall gain that is received from a system over some finite time interval. When transient measures are integrated over the time interval 0 to t, then y of t can be given as integration 0 to t r suffix xs of ds. Now we are moving into the one type of renewal process, that is called alternative renewal process. Let xi's are IID random variable which constitute on times, and yi's are IID random variables which constitutes off times. Assume that mean is exists and it is finite, and x plus y has the distribution capital F. Suppose that the renewal occurs at the end of every xi's, whereas no arrivals at the end of every yi's. Assume that xi's and yi's are independent random variables also. Then the xi plus yi are called the alternative renewal process. See the example for this situation. A machine works for the time x1 and then breaks down and has to be repaired, which takes a time y1, then works for the time x2, then it is down for a time y2, that's a second repair time, and so on. So xi's are nothing but the machine works, and yi's are nothing but the repair time. If you suppose that the machine is good as new after each repair, then this constitutes a alternative renewal process. So this is the example of alternative renewal process with the proper assumptions. Now we are moving into the next renewal processes, that is delayed renewal process. It is not always reasonable to insist that the first renewal occurs at time s0, that is equal to 0 in the origin itself. It's a time 0 itself. For instance, in applications where the occurrence are not or at times when a component of a system must be replaced. One might well be interested in situations where there is already a working component in place at time 0. For this reason, we defined a delayed renewal process to be a sequence S0, S1, S2 and so on, where Sn is nothing but S0 plus a summation of first n xi's, and the inter-arrival times xi's are positive and IID random variables as in the ordinary renewal process. And the initial delay S0, which is greater than or equal to 0, that is independent of inter-arrival times xi's. Notice that the distribution of initial delay random variable x0 is not recorded to be the same as that of the inter-arrival time random variables xi's. Hence, a delayed renewal process is a renewal process in which the first arrival time x1 is independently and is allowed to have a different distribution, that is f1. The distribution of all remaining IID random variables, that distribution is capital F. So the f1 is different from f. The x1 is equal to t1, that is nothing but the delay. When there is no such delay, then x1 is also distributed in the same way, so the distribution of x1 is capital F as usual. Then the renewal process is said to be a non-delayed version. Now we are discussing the central limit theorem on the renewal process. As n tends to infinity, the random variable s suffix n, that is nothing but the nth time renewal, minus n times mu divided by sigma times square root of n will be normal distribution with the mean 0 and variance 1. So this convergence takes place in distribution. So this is a weak distribution, weak convergence. So as n tends to infinity, the random variable Sn and the mean of Sn is n times mu, and the variance of Sn is sigma square n, and the random variable minus their mean divided by the standard deviation is normal distributed with the mean 0 and variance 1 as n tends to infinity. As n tends to infinity, the n of t, that counting process, it's a renewal process, becomes a normal distribution with the mean t divided by mu and the variance sigma square t divided by mu cube, where mu is the mean of interarrival time. As a t tends to infinity, the random variable n of t minus t by mu divided by sigma times square root of t by mu cube will be normal distribution with the mean 0 and the variance 1. So this is also the convergence in distribution. Now we are going to discuss the long run properties of renewal process. There are two types of long run properties. One is to obtain the long run average of the quantity of interest. The other one is to obtain the pointwise limit. For example, the long run average of age, that is limit t tends to infinity, the integration 0 to t of a of s is the age divided by t, while the pointwise limit of the expected age, that is limit t tends to infinity, expectation of a of t. One can study the average number of renewals per unit time in the long run. It is called the long run renewal rate. For a renewal process having a distribution f for the interarrival times, the long run renewal rate is nothing but a limit t tends to infinity n of t divided by t. That will be 1 divided by mu with the probability 1, where mu is nothing but the mean of interarrival time. Since s suffix n of t is a last renewal time prior to t and s suffix n of t plus 1 is the first renewal time after t, we know the relation of s of n of t with the s of n of t plus 1, and that lies, the t lies between those two renewal times. You can divide by t, you can divide by n of t. Therefore, s of n of t divided by n of t less than or equal to t divided by n of t, that is less than or equal to s of n plus t plus 1 divided by n of t. Now we can evaluate the first one, the s of n of t divided by n of t limit t tends to infinity. That is nothing but, the numerator is nothing but the summation of xi's till n of t, denominator is n of t. And that is nothing but expectation of x. In a long run, the summation of x1, x2 till x of n of t divided by n of t, that is nothing but the expectation of x. That is same as the mu with the probability 1. And similarly, one can evaluate the last value, that is s of n of t plus 1 divided by n of t, that is also will be mu with the probability 1. Since t lies between s of n of t and s of n of t plus 1 and throughout divided by n of t in all three, therefore, as limit t tends to infinity, n of t divided by t will be 1 divided by mu with the probability. This is the last part of in this lecture, that is renewal limits theorems. We are going to discuss only 3 important renewal theorems without proof. The first one is elementary renewal theorem. It states that the basic limit in the law of large numbers in mean as well as with the probability 1. For a renewal process having the mean inter-arrival time where mu lies between 0 to infinity, the limit t tends to infinity, the expectation of n of t divided by t, that is nothing but a limit t tends to infinity of expectation of n of t is nothing but the renewal function capital M of t divided by t, that is same as 1 divided by mu. Since n of t goes to infinity almost surely, and by the strong law of renewal process we get this result. This result shows that for large t, the number of renewals per unit time converges to 1 divided by mu. That is, the limiting mean arrival rate of arrivals, mean average rate of arrivals is 1 by mu. That is, the limiting mean average rate of arrivals is 1 by mu. Note that the limit value of a sequence of random variables is not same as the limit value of a sequence of mean of random variables. This is true in general also. Here we discuss particularly for renewal process. The n of t is a random variable. Expectation of n of t for fixed t is a constant. So, here we are finding limit t tends to infinity, the expectation of n of t divided by t, that is 1 by mu. If you consider the reward renewal process R of t, when the expectation of R is finite as well as expectation of x is finite, limit t tends to infinity, the expectation of R of t divided by t, that will tends to expectation of R divided by expectation of x using the elementary renewal theorem. If you know the value of expectation of R and if you know the value of expectation of x, as a t tends to infinity, expectation of R of t divided by t will be expectation of R divided by expectation of x. So, this result we have used it in one example. The asymptotic property of a reward renewal process is as follows. As a t tends to infinity, the R of t divided by t will converge to expectation of R by expectation of x with the probability 1. This is called the asymptotic property of a reward renewal process. Both will be used in applications. Before moving into the next renewal limit theorem, we need the definition of lattice. A non-negative random variable x is said to be a lattice if there exists d greater than or equal to 0 such that the probability of x equal to n times d for n is varies from 0 to infinity, that will be 1. If this condition is satisfied, then we say the D is called the period and the corresponding random variable is called a lattice. The largest D having this property is said to be a period of X. If X is lattice and X has a distribution F, then we say the F is lattice. For instance, X follows a Poisson distribution with the mean lambda, then X is lattice with the period 1. Because the summation n is equal to 0 to infinity, the probability of X is equal to n is equal to 1. That means the D will be 1. Whereas in the second example, if P of probability of X equal to square root of 2 is equal to 0.5 and the probability of X equal to square root of 3 is 0.5, then you cannot find a D such that summation of n is equal to 0 to infinity probability of X equal to n times D is equal to 1. This condition is not satisfied by the second example, therefore X is not lattice. So using lattice we are going to discuss the second renewal limit theorem, that is a key renewal theorem. Let xt be a renewal process with the continuous interarrival time non-lattice distribution function f with the mean mu. So this is a renewal process and has an interarrival time which is the distribution is a non-lattice and it has a finite mean. If h is an integrable and non-increasing function, as a t tends to infinity, the integration of 0 to t h of t minus x integration with respect to the renewal function capital M of t will tends to 1 divided by mu the integration 0 to infinity h of x dx. So this type of integral comes in the integral equation which we discuss in the renewal equation. So as a t tends to infinity, whenever the integrand is a integrable and non-decreasing function and integration is with respect to the renewal function and the corresponding renewal process has a non-lattice distribution for the interarrival time, then as a t tends to infinity, this integral will be 1 divided by mu times integral 0 to infinity h of x dx, whenever h is a integrable and non-decreasing function. We are going to consider one simple example for that. Let yt be the xs at time t, and we know that the expectation of xs is nothing but h of t plus integration 0 to t h of t minus x integration with respect to the renewal function, where h of t is nothing but t to infinity x minus t integration with respect to the distribution function f. Therefore, limit t tends to infinity, the expectation of xs will be limit t tends to infinity of the integration 0 to t h of t minus x dmx, since the first value will be 0 as t tends to infinity. Assume that the second moment of the interarrival time is finite, then h of t is a integrable and non-increasing function. Therefore, you can use the key renewal theorem by making additional assumption f is non-lattice distribution. Now we can apply the key renewal theorem to obtain the limiting mean xs. After simplification, one can get a limit t tends to infinity, expectation of y of t is same as expectation of x square divided by 2 times expectation of x. So to get this value, we made assumption the second moment of interarrival time is finite, Hence h of t is integrable and non-increasing function, and also we made assumption f is a non-lattice distribution. Hence we are able to apply the renewal theorem and getting the limiting mean excess as a expectation of x square divided by 2 times expectation of x. The last renewal limit theorem is Blackwell's theorem. Let mt be the renewal function, and the Blackwell theorem says asymptotically the expected number of renewals in an interval is proportional to the length of the interval. That is, the proportionality constant is 1 divided by mu. If f is not a lattice, then limit t tends to infinity, the renewal function evaluated at t plus h minus renewal function at t is same as the interval length multiplied by 1 by mu. 1 by mu is a proportionality constant, the length is h, because you are evaluating the renewal function between the interval t to t plus h. If f is a lattice distribution with the period d, then the limit t tends to infinity, the expected number of renewals at nd will be t divided by mu, because the probability of number of renewals at nd will be d by mu, and the number of renewals will be either 1 or 0. Therefore, the limit t tends to infinity, expected number of renewals at nd is d by mu. Here is the reference for lecture 2 in module 8.